In the last section, we spoke about how the range of values for our bounciness is absolutely minuscule compared to the range of values for our drop position. And so chances are that when we run our analysis right now, the bounciness factor is basically having like no effect on our actual output. So in this section, we're going to learn about two strategies that we can use to address this. All right, so here's our two strategies. We can normalize our data and we can standardize our data. Both these strategies are almost identical. The only big difference between them is the formula that we use. So with normalization, we take our original data, which might arrange in values for, say, just our drop position from 300 to 600. We only consider one feature at a time. So we would only apply normalization to drop position by itself, then we would apply it to bounciness, then to ball size, and so on. With normalization, we're going to try to proportionally scale all of our numbers between 0 and 1. So for example, the data point right here at 300 would be assigned a new value of 0, and the point at 600 over here at the very top end would be assigned a data point of 1. Standardization is very similar, but instead of bounding numbers between 0 and 1, we try to base all of our numbers around a value of 0, and then we get what is called a normal distribution around that of -1 and 1 standard deviations. So with standardization, we're not necessarily capping values at 0 or 1. With standardization, we can very easily have values that go beyond that single 1 standard deviation, as would probably be the case over here with the 600. Now we're going to talk about standardization a lot later on inside the course because it's a fantastic method with some of the algorithms we're going to use later on. But for right now, we're just going to concern ourselves with normalization. Now applying this strategy of normalization, of getting numbers between 0 and 1, uses what is called a min-max method. So with the min-max, we're going to look at one feature set at a time. So like just our ball drop position, and then just the bounciness, and just the ball size. We're going to look at each of those features, and we're going to find the minimum value and the maximum value. We're then going to apply this equation right here for every value in that data set. Now this equation right here is kind of a little bit unclear, especially with these really long words that I'm using, so we'll walk through an actual example of this in just a second. Okay, so here's some examples of it in action. Now, that's not what I'm talking about when I say we'll go through this in a second. We're going to actually write the code out for this in just a second. That's what I'm talking about. But just very quickly as examples, if we have drop positions with these values right here, the minimum value would be 150, and the maximum value would be 650 right there. And so we would use these min and max values to scale each of these values, which would then make them scale or range between 0 and 1. We could then do the same thing for bounciness as well. Note how we apply this to bounciness. We are selecting our min and max values from the bounciness data set only this feature, one feature at a time. And so at the end of the day, after we apply the scaling to every separate feature, they're all going to range in values from 0 and 1. And so in theory, they're all going to apply to our outcome, in this case, which bucket the ball falls into, equally. Okay, let's very quickly look at an example of this in that nice little code editor. So quick reminder, here's the link to it. We'll just do a very quick example. Okay, I'm going to open up a new browser tab and navigate over there. Now let's consider some arbitrary points. Let's do like, say, 200, 150, 650, and 430. And those are actually the same data points that I just showed you in this diagram over here. Same one. So we should get the same result right there. So the first thing we have to do is find the min and max values in this array of numbers. Now, of course, Lodash has our back for this. We don't have to write any for loops or anything like that. So we can do const min is _.min points, and const max is .max points. We'll then map over our points array, and for every point, we're going to run that min-max formula. So I will return point minus min divided by max minus min, like so. And I see the output up here. So we get 0.1, 0, 1, and 0.56. So that's our scaled output. Or another way of saying it is normalized. You will see the terms scaling and normalization used somewhat interchangeably. For whatever reason, very similar. You see them interchangeably used in a lot of different blog posts and what have you. But standardization definitely is a very different beast. Now, the last thing you might be curious about, you might be thinking to yourself, Stephen, how does this not just dramatically change the results of our k-nearest neighbor algorithm? How does this not just absolutely nuke everything we're doing? We're just arbitrarily dividing numbers here. How does it not going to somehow change what we're getting as an output? Well, I want you to remember exactly how k-nearest neighbor, the algorithm itself, works. Let's walk through a quick example using only drop position of k-nearest neighbor, and then we'll take a look at it with some scaled numbers as well. And you're going to see that the output does not change and really cannot change. So in the version right here that you see that has no scaling whatsoever applied, we've got our drop positions that range from 40 all the way up to about 425. So the first thing, and then we want to make a prediction about a observation point at 200. So we would take all these observations right here, and we would subtract 200. So 40 minus 200, and then absolute value of that would be 160. We get 50, 150, 225. We would then sort all these based on their distances, and we end up with red, green, blue, purple. Now let's go through the same process, but we're going to scale these numbers during this distances step as well. Okay, so same stuff that you see right here. All we've done is scaled the numbers in this intermediate step. So now our values range from 0 to 1. Notice how we are also going to scale the value of our prediction point as well. So we don't just take our prediction point of like 200 pixels and throw it in here. We do our min-max formula based on this data set over here, and then we apply it to our our point that we're trying to predict right here as well. So if we run min-max with these data points and then apply it to the 200, we would end up with 0.415. So with that in mind, we can now go through the same process where we scale each of these training values and then subtract 0.415 from each of them. So we would end up with 0.41, 0.129, and so on. And then when we try to sort those, we end up with red, green, blue, purple, which is identical. Here, I'll tab back and forth, identical to what we had before. So it's irrelevant that we scale these numbers. Doesn't make a difference. No change whatsoever. The outcome is always going to be exactly the same because these are all distances that are relative to the point that we're trying to predict. Okay, so hopefully this makes a little bit more sense. Let's take a quick pause right here, and then when we come back to the next section, we're going to start to implement min-max on our project. So quick pause, and I'll see you in just a minute.